Good morning, and welcome to this, the 11th edition of CAOS. CAOS stands for Concepts, Actions, and Objects, but some people who don't know how to spell in English thought it sounded like another interesting word in English, chaotic, and there's nothing chaotic about these meetings. There's lots of discussion, which is a great part of CAOS. Thank you all for coming, and I just have one brief announcement before starting the day. One of the speakers, Tom Griffith, will not be able to come. He had some injury to his arm, his nerve in his arm, and has to have surgery, and so he couldn't come. And we have coerced another person to take his place. She usually travels with her slides, just in case she has to be coerced into giving a talk. Sharon Thompson-Schill will take Tom's place. This is a meeting that's been going on, as I said, for 11 years. It's a meeting that some of us are really excited about. It was started 11 years ago. At the time, it was just 4 organizers, Mel Goodale, Alex Martin, Brad Mahon, and myself. And then we realized that we weren't able to do this job properly, and so we recruited a few other people to help us with the work. Marius Pilin and Sharon Thompson-Schill, and I think it's everybody. I've not left anyone. These meetings are planned the last day of the meeting, the last day of CAOS. We plan next year's meeting, and we hope to do it again this year. The financial situation is not so great as it used to be a few years ago, but we're still going to try and see if we can schedule the 12th edition of CAOS for next year. So if anyone has any good suggestions to throw away about topics for next year, we welcome. Pass them on to anyone in the committee. I have no other announcements, I don't think. Remember the social dinner, but I think everyone is aware of that. Remember the posters that we have downstairs, and also remember that there is a workshop planned in October to celebrate the 10th anniversary of foundation of the Center for Mind-Brain Sciences, CIMeC. And again, you're all invited. I hope some of you can come. I'll send you students. There will be about 20 speakers here. I am not involved in the organizing, but I've heard there are about 20 speakers who have been invited, and should be a fun meeting. So last bit of information. We're a bit late to start. I apologize. I've also been talking too much. The speakers have 45 minutes, and we'll try and hold them to the 45 minutes so that we can have half an hour of discussion. Usually the discussion is dominated by a few rather contentious people in the front seats. Really welcome and hope that people in the rows in the back speak up, put up your hands. I'll be chairing the session, so I'll be looking for hands out in the depth rather than the front first. So please participate. Don't be embarrassed. That's it. So the first speaker this morning is an old CIMeC person, Angelica Lignau. She's now a professor in the slide's not up yet, Royal Holloway, University of London. Angelica was my first postdoc here at CIMeC. I think years ago, 10 years ago. And I quickly convinced her that she should change field, and she did, and I learned a lot. She changed into something I knew nothing about, which was the best way to have a postdoc, because then I could learn from Angelica, and I learned a lot. So Angelica is the first speaker.
Thank you very much. Oh yeah, just need to put on my slides. Can everybody hear me? Yes? Okay. okay, I hope I won't get entangled in this cable, so that will be an interesting moment. Thanks. So first of all, it's a great honor for me to talk at this conference that I attended for so many years, and I'm very much looking forward. So today I'm going to talk to tell you about the topic that Afonso convinced me to study in more depth, the representation of actions in the human brain. So our life is full of actions, so we are able to easily recognize that these different actions, even though they are visually very different, they all depict the same action. Is it possible to lower the light a bit, because I think then it's easier to see the images? Could someone do that? No? Well, okay, let's see whether this happens. So the important point to notice here is that despite the fact that very different objects and very different agents are involved in all these images, we don't find it difficult to see that all of these images refer to the same action, namely feeding. At the same time, we also find it easy to tell that these two actions on the top refer to another action in comparison to the two images on the bottom, which you might describe as transporting something, despite the fact that the two images on the left have a lot of visual similarity and objects and agents in common, like the cow and the people here and the hay, and the same applies to the actions on the right. So despite similarity of the visual features of these actions, we do not classify them according to visual similarity, but rather to their meaning. And the question is, how do we achieve this task? One way to think about that used to be that these more abstract representations that generalize across low-level aspects are represented in the motor system, in particular in the IPL and the ventral premotor cortex, whereas it used to, that should have been read. Whereas we used to think about higher level about representations in visual and temporal cortex to present a visual analysis of the action that does not necessarily contain such generalization across features. So in the first part of the talk, I would like to present you a couple of studies in which we followed this up more closely. So namely to identify areas that contain such abstract action representations. So the specific aim here was to identify areas that are able to distinguish between different actions, but at the same time show generalization across the way in which we perform these actions. So I'm assuming that most of the people in this auditorium are familiar with MBPA. I'm just seeing Jim Haxby coming into the auditorium that has been very influential in this field. So what we typically do when we're extracting information from an area of interest is that we're comparing the amplitude of the bold response. And if you, in this toy example, if we do that for two different actions, usually we wouldn't see a difference in terms of the bold amplitude. However, we can exploit the fact that there's information in the patterns of brain activity. And now we can train a classifier to recognize those differences in the patterns and then apply those algorithms to a new, fresh set of data and ask the classifier whether the presented action corresponds to category A or B. And so this is the logic that we are using, that we've been using in many of these studies. That's why I introduced it here. So the first study that I want to present to you is a study that we carried out with Moritz Wurm, who's sitting here as well, here at CIMeC. And what we did is we manipulated the action, which was either cutting an object or peeling an object, and we manipulated the object on which this action was performed, namely apples or potatoes. You see where we're coming from. We're living in Trentino, lots of apples and potatoes here. And so what we did is in a block design, we presented participants with those videos. So they didn't perform actions, they saw those videos. And in different blocks, they had to perform different tasks. So in the action task, they had to press a button whenever the same action was repeated. Whereas in the object task, they had to press a button whenever the same object was repeated. And the reason for that manipulation was that we wanted to see whether any representations that we're finding are there also if we don't pay attention to the action, or whether they are actually coming about automatically. So what we then did is, as I said earlier, we trained the classifier to distinguish between cutting and peeling, for example, the apple. And now we did that for two different levels. For the concrete level, that is depicted here in red, is we trained the classifier to distinguish between the two actions on the same object as the object that we used to test the classifier. So train on the apple, test on the apple, and so forth. Whereas for the blue condition, the abstract condition in this case, we trained the classifier on one object and tested the classifier on the other object. Okay, so what we then did is we pulled out the data from the key regions that you also typically see in univariate analyses that is depicted here. So the typical action observation network consisting of the ventral premotor, IPL, and the LOTC. And within those regions, we then examined the performance of the classifier. So I'm not presenting you here the amplitude of the bold response, but the accuracy of the classifier. And since we have two actions, chance performance is 50%. So what you see here is on the y-axis the performance of the classifier, and on the x-axis the different regions of interest. And in dark red you see the concrete conditions, so training and testing on the same object. And the bright red bars the dark red corresponds to the action task, so when participants actually pay attention to the action, whereas the bright red corresponds to the object task when participants pay attention to the object. And what you see here in left ventral premotor cortex, both in the left and right hemisphere, is that you can distinguish between cutting and peeling, but only if you pay attention to the action, and only when you train and test the classifier on the same object. As soon as you move to the other object, or if you're not paying attention to the action, you can no longer distinguish between cutting and peeling. So it's a rather concrete representation here. How about the IPL, or IRPS in this case? Here you can see that in the left hemisphere, you can distinguish between cutting and peeling both when you're paying attention to the action and when you're paying attention to the object. So it's a generalization across the task, if you want. And in the right hemisphere, you can also distinguish between cutting and peeling when you're training and testing the classifier on two different objects. So a bit more of a generalization here, whereas the highest degree of generalization we observed in the left LOTC, where we found that no matter whether you're paying attention to the action or the object, and no matter whether you're training and testing the classifier on the same or two different objects, you can distinguish between cutting and peeling. Okay, so that was the first step for us to think, okay, there's something in here in the LOTC, and we seem to see a gradient here from ventral premotor cortex up to the LOTC. Can we actually see that also in other actions? Because admittedly, cutting and peeling is not a very wide range of actions, right? So we were interested in seeing whether we can replicate that in other actions as well. At this moment, I need to take a sip of water. If anyone has a question, it would be a good moment. No? Okay. So how about other actions? So what we did next is to move to other actions, in this case, opening and closing actions. And we the videos that we used were depicting actions that were using two different objects. So in this case, a bottle or container. And now the interesting thing was that this allowed us to look into three different levels of representation. So in the most concrete, at the most concrete level, what you see here in what I see as red is the most concrete level where we train and test the classifier on exactly the same object. So that means the opening and closing not only perceptually was very similar, but also the kinematics were similar in the sense that the same object required either a tilting or lifting movement. So both visually and in terms of kinematics, these actions were very, very similar. At an intermediate level, what we did is we trained and tested the classifier on the same object class, but on different exemplars that required different kinematics. In this case, lifting the cap versus tilting. No, actually, this was tilting the cap and this was lifting the cap, and we did it in both directions. So this would show a generalization across the kinematics, whereas the highest level that we tested in this experiment was to train the classifier on one object class, for example, the bottles, and test the classifier on the other object class, in this case, the container, and vice versa. And again, we asked the question, in which of these areas are we able to distinguish between opening and closing, irrespective of, say, the kinematics or the object class, okay? So this is what we found, a very similar way of depicting the data. So here in left and right ventral premotor cortex, in red, again, the concrete level, so training and testing on exactly the same exemplars, but different data sets, of course. We can distinguish between opening and closing, but we cannot distinguish between opening and closing if we vary the kinematics or if we vary the object class. If we go to the IPL, we can decode at all three levels, so both at the concrete level, also when we manipulate the kinematics, and also if we manipulate the object class. And in the OTC, you find the same, but the classification performance is even higher. So the trend is very, very similar to what you've seen in the previous experiment, but for different tasks and different stimuli and different types of generalization. So that made us confident that what we saw in the first study is replicable. At this point, you might, of course, wonder, well, you're presenting us three regions here. Maybe you overlooked some very important areas. Of course, we also did the same analysis using a searchlight analysis, and this is just to show you briefly that the black doesn't look very pretty, but okay. It is red on my slides. So the important thing is what you see here in blue and green is the abstract and the intermediate level, which you see here on the inflated hemisphere of both hemispheres, is that there's really nothing at the intermediate and abstract level anterior to the central sulcus. So you essentially see it in the IPL and in the OTC. That essentially replicates what I showed you in the Roy analysis. And that is what we see across many studies. We've replicated this a number of times now. So to provide you with an interim summary at this point, we see a generalization across kinematics, objects, and task in the LOTC. We see a generalization across kinematics and objects in the IPL, and no signs of generalization across these aspects in PMV, suggesting a rather concrete representation in that area. So at this point, sometimes people ask me, so did you try that also for movements that participants actually perform? And so far, I always had to say, yeah, we're planning to do that. We don't know yet, but in the meantime, we did that, thanks to Luca Turella, who's probably also somewhere here. Yes, there he is. So, so in the next project that I want to present to you, we looked into the generalization across the way in which we perform actions for actions that participants actually perform inside the scanner, which for various reasons is not straightforward. So Luca spent a lot of time on building this device here inside the scanner made of plexiglass, on which he was able to attach wooden objects that you can actually take inside the scanner. So thanks to Luca for figuring this all out. And so here's the start position where he can record the onset of the movement, and there's a camera outside the scanner board to record the precision of the movement, such that we really have a good understanding of what is going on inside the scanner. And now what he did inside the scanner is that, or what we manipulated inside the scanner was the action. So participants either performed a precision grip on the wooden object inside the scanner or a whole hand grip. And they did that with the right hand or the left hand, and they did that with two different wrist orientations. So either with an upright wrist orientation or with a tilted wrist orientation by 90 degrees, okay? And now, logically very similar to what I just presented to you for observation, we now looked at different levels of representation here. So at the very concrete level, we trained the data to distinguish between whole hand grip and precision grip with one particular effector and one particular wrist orientation. And we tested the classifier on exactly the same. So the same wrist orientation, the same effector, but on a fresh data set. So this is what we call the concrete level here. At the intermediate level, we looked into the generalization across wrist orientation, so distinguishing between whole hand grip and precision grip within the effector, but across wrist orientation. And at the most abstract level, we trained the classifier to distinguish between whole hand grip and precision grip across effector and across wrist orientation. Yes? They did not see their hands. On purpose, we distinguished what they saw from, we wanted to make sure that they did not see their hands, because otherwise you don't know, is whatever we are seeing a representation of their own seen hand or what they are doing, and we wanted to dissociate that here. So they only saw the screen above them, and on the screen they had a simple instruction of the fixation cross that indicated which movement to perform. That was all. Yeah, thanks for the question, good point. Okay, so just a sip of water. So what you see on the next slide, or on this slide, is the outcome of the concrete action decoding. So within the same effector and the same wrist orientation for the left and right hand. And what you see here is that there's a huge network of areas in both the left and right hemisphere where you can decode between whole hand grip and precision grip, which is maybe not that surprising. The more interesting aspects are, of course, the intermediate and abstract levels. So this is what you see on the next slide. So this is what you see when you're trying to decode while generalizing across the wrist orientation. So you see that this is possible for the left hand and parietal cortex, and also in premotor regions, and a bit more for the right hand than for the left hand, which is perhaps not that surprising. So you see that both in parietal, premotor regions, and a bit in the occipitotemporal regions. How about the most abstract levels? So generalizing across wrist orientation and effector. And this might or might not be surprising for you. The highest generalization we find in the IPL and the LOTC over here. And this is more in the left hemisphere than for the right hemisphere, whereas there's very little going on in premotor and frontal regions. Luca then had this idea to also look for the, yes? Well, it's at the very posterior boundary of LOTC, right? Yeah. We might discuss where the exact boundaries are, because that's a gray zone, right? But it's not frontal, it's not premotor. That for sure. Okay, so then what we did next is to look into the conjunction between these three levels, between the most abstract, the intermediate, and the highest level of generalization. And this is what we found. So this is a conjunction between the most concrete level, so within the wrist orientation and within the effector in the left hand and the right hand. And here you find that the conjunction for these two levels is found both in the parietal cortex and premotor cortex, both in the left and right hand. Whereas the conjunction for level 2 and 3, so the generalization across wrist orientation and the generalization across wrist orientation and effector, is circumscribed here in parietal cortex, but not in premotor cortex, which again I think adds an interesting additional description of these results. So a short recap on those results. What we find in motor and premotor cortex for executed actions is a joint encoding of concrete hand actions together with abstract information about their goals, so irrespective of wrist orientation, but only within the effector, no generalization across the effector. Whereas in the parietal lobe, we find goal encoding within and across the hands. And in the posterior temporal cortex, we find an effector-independent goal encoding, but no convergence between the effector-dependent with the effector-dependent goal encoding, right? Remember, it didn't show up in the conjunction maps. Okay, so if there are no questions on this aspect, I'd like to switch gears a little bit and move on to a slightly related topic. And that is the question, can we actually distinguish between action functions and states of objects, right? So many of the actions that we're performing do not only consist of the action itself, but also on the state in which we are bringing the object, right? So if you think of building a house, when you're building a house, at the beginning you have stones and concrete, and at the end you have a house. So what is it that we're looking at here in IPL and LOTC? Is it the function itself, or the change of the state of the object, or a combination of these? More formally, we wanted to see whether we can distinguish between the representation of the function and which changes an initial state into a final desired end state, and the states of the object itself. So that's not straightforward, so we spent quite a bit of time during a visit of Udi Zahari and his postdocs we wrote when we were still at CIMeC, thinking about how we could best do that, and we spent hours and hours talking about this until we came up with the following. So we performed 2 different experiments here in the same participants subsequently. So what we did in the first experiment is we presented participants with static images of objects that were in a particular state. And the state that we chose was either open, so for example this open dustbin, or close. Think of this closed dustbin, right? And I'm going to show you more examples in a second. Whereas in experiment 2, we presented participants with videos. And in these videos, again, we saw similar objects. For example, an object that is opened from a closed state to an open state, or vice versa, from a closed state to from an open state to a closed state. And we had 2 main conditions here in this second part of the experiment, namely that the states of the object were either visible, as you can see here, or they were invisible. So you only saw the manipulation of the object, but you couldn't see the end state. You couldn't see the initial state, and you couldn't see the end state. You could only infer that, right? And so we took many different exemplars, always of the same actions, opening and closing, and we took them from different viewing angles and in different contexts to make sure that we have a lot of perceptual variability. And so the logic was that in order to get at the key of action functions, we trained a classifier to distinguish between opening and closing in the visible condition when the initial and end state of the object were visible. And we tested the classifier on the invisible condition when the object states were not visible. And we did the same from invisible to visible. And the idea here was that any area that shows that kind of generalization cannot be driven by the perception of the end state itself, because in the invisible condition, the end state is not there. So this is what we did for the functions, whereas for the object states, we tried to distinguish between opened and closed still images for training, and then tested the classifier on the videos that showed the initial and end state, so the visible condition. And we did the same, of course, in the opposite direction, and then computed the average accuracy. And I'm going to show you the searchlight analysis here in green. So this is what we see for the decoding from the visible to the invisible condition. So a generalization across whether or not you see the initial and the end state. And you find here again that this in particular reveals the LOTC and a little bit in the IPL, in particular in the right hemisphere, whereas for the object states, you find that we find this in more frontal regions here at the level of the IFG. So that is, I think, an interesting dissociation between functions and object states. Okay, this is what I basically just said. So we find a distinction between the encoding of action functions and the encoding of the initial object state. Yes?
Could you go across the
Yeah, that would be nice to do, to be honest, and we've discussed this a lot. The problem is, as soon as you do that, of course, you're giving up a lot of your power because you're using fewer data. With this particular data set, because there were so many conditions, unfortunately, we didn't have the power to do that, but it would be very interesting for a follow-up. I agree. Okay, so how am I doing with time, Alfonso? 20 minutes, okay, perfect. So that gives me time to talk about the third topic, the third and last topic of my talk. So as I tried to indicate at the very beginning of my talk, it is likely that in order to show this generalization across the way we perform actions, it's likely that we categorize actions. Very similar points have been made for the representation of objects, but much less is known about the categorization of actions. So what we did in this project that I'm going to present you now is to try to see whether we can distinguish between key action categories that are likely to be present. And what we did for that is we manipulated, so we used 8 different actions, and what we manipulated here was whether these actions were social in this, and the way we define social was whether or not the action was directed towards another person, as in the example of giving an object to another person or taking an object away from another person, whereas non-social were actions that were again performed in the presence of another person, but the presence of the other person was not crucial for the performance of that action. In this case, opening and closing, or closing an object. And the reason why we always had the other person present is obvious, because we didn't want to have low-level features determining the distinction between social and non-social actions, obviously. And we did that both for transitive actions, so actions that were performed on an object, and on intransitive actions, in this case, agree, disagree, and stroke, scratch, which was performed on the actor's own body. So we had this 2x2x2 design, social, non-social, actually 2x2 design, social, non-social, transitive, intransitive actions. Okay, and so again, we manipulated a lot of the perceptual variability. So we manipulated the position of the key actor. We manipulated the kind of objects on which these actions were performed. We manipulated the viewing angle, and we manipulated the context. Was performed either in an office or breakfast context. And so what you see here is just also to show the relation to the previous studies that I showed you. This is the multi-class decoding of all the 8 actions against the, of each of the 8 actions against the remaining 7 actions. And again, you see a very similar network of areas showing up as in the previous studies, indicating that what we saw before in the other actions also generalize for these other actions. And more interesting for the question of whether we can distinguish between different action categories is that we carried out a representational dissimilarity analysis. So for that, Moritz asked participants after the experiment to rate each of these actions on 2 different scales, namely on sociality and transitivity. So to the degree to which another person was relevant to perform that action, and the degree to which another object was relevant to perform those actions. And from that, we were able to construct these representational dissimilarity matrices for transitivity and sociality. And now we were able to use those behavioral matrices to see where in the brain do we find the highest correspondence between the neural dissimilarity and the behavioral dissimilarity. And we did that focusing on the lateral occipitotemporal cortex. So what you see here is a stripe that we extracted from that area. And now what you will see in a second is plotting the results as a function of the position on this stripe here. And in red you see, or you should see the correlation with the sociality model, so from dorsal to more ventral regions, which peaks here in this more dorsal portion, whereas in blue you see the correlation with the transitivity model, which peaks in a more ventral portion at the, oh, wait a second, I don't want to connect to iCloud, sorry. Okay, so you see this indicates indeed a distinction between the sociality model and the transitivity model, and we see a very similar distinction here in the right hemisphere. And if you plot that as a dendrogram, you see essentially the same thing, but visualized in a different way, that the more dorsal portion of the LOTC is organized according to sociality, whereas the more ventral portion is organized more towards transitivity, indicating that there's indeed this dorsal to ventral gradient from sociality to transitivity. So a brief interim discussion on that aspect. So I just said we find this dorsal-ventral distinction of actions, and I think I don't have to repeat that. So the very final project that I want to tell you is just came fresh out of the lab, and we've done that actually in London. So the question we ask here, our daily life consists of many different actions, perhaps even more variable than the actions I've shown to you before, and they take place in many different contexts, and they involve different objects, and some of them involve another person, others don't. And the question is, can we somehow depict the relation and the meaning between those actions while also accounting for the manipulation or the differences in all these other aspects, such as the context and the body parts that are involved and the objects that are involved. And that's, of course, a tricky business. So what we did is we took, based on quite intensive pilot studies, we settled down on 28 daily life activities that most of us do on a regular basis, perhaps not dancing, but some of us. And each of these actions we took in different contexts. Again, we had two different actresses. One of my PhD students here and one of my master student took lots of days to take these photos, and yes, different viewing angles and different objects. And so again, we had a lot of perceptual variability. And what we then did is we used a technique called inverse multidimensional scaling. This has been developed by Nico Krieger's quarter. So essentially, you're assigning all the actions on a circle on the screen, and participants have to drag and drop these actions on the screen with a mouse according to the perceived similarity, according to certain aspects. So the most obvious aspect that we used was the similarity in terms of the meaning of these actions. But of course, you can do that also with respect to the similarity according to the movements that are involved, the objects that are involved, the context in which this typically happens, and the body parts that are typically performed. Now, naturally, these different aspects go together, so I wasn't really expecting that they are clearly dissociable, but they should correlate, but they should explain some slightly different aspects in different parts of the brain. What you see here is the result just as an example of the semantic similarity, now across a group of 20 participants. And what you see here, it's perhaps too small to see, but I will show you in a moment more clearly, is that they tend to cluster these actions according to meaningful categories. So this is a dendrogram plot of the same data that I just showed to you. And I highlighted here, ooh, the colors are awful. So I highlighted here the clusters into which they fall. So this seems here like clustering according to food-related actions, body-related actions, actions related to leisure, such as sports or reading, then actions according to locomotion. So participants use those categories to assign the meaning. And the question is, where in the brain can we find a similar organization according to those ratings that participants made outside the scanner after the experiment? And again, similar to the project that I presented to you before, is we used representational similarity analysis, now using these different models that I just talked about. And here's an example result, a searchlight analysis using the semantic model as a predictor. And it's perhaps not surprising to see this network of areas revealed by this representational similarity analysis. And it's a bit pointless now to compare all those searchlight maps because, as I said, these models are correlated with each other. But what we can do in each of these regions is to see which of the models explain the data best. And this is the last slide that I want to present on that project. And here you see, again, I picked out the three key regions I talked about before, the LOTC, the IPL, and the ventral premotor cortex. And what you see here is that in the LOTC, you find that the body part model, so the similarity in terms of the body parts that are involved, and the movement model, and the semantic model, and the object model all explain a portion of the data, body and movement more than semantic and objects. We have not yet tried to break this down into smaller sub-portions. I'm assuming that if you look into a gradient inside the LOTC, these results also might vary according to that. We haven't done that yet, if you are wondering. Whereas in the IPL as a whole, what we see here is that the movement model explains the data best, whereas in the ventral premotor cortex, we see that the movement model and the context model gives the best explanation. So this is where we are with this project. There are many more analyses coming up for that. And yeah, so a brief summary on that project. So we saw that the LOTC shows the highest correlations with the body, movement, semantic, and object models. The IPL, the highest correlation with the movement model, and the PMV, the highest correlation with the movement and context model. So let's try to put that all onto a map to wrap up what I talked about. So what I showed in the first part of the talk is that I hope that I convinced you that we have good reasons to believe that the LOTC and the IPL contain very abstract representations, both for observed actions, but also to a certain degree for executed actions, whereas the ventral premotor cortex contains rather concrete action representations, and this is what we see across a number of studies. I've showed you data indicating that what we see in the LOTC and the IPL is more related to the function itself, whereas the ventral premotor cortex slash IFG contains or is more sensitive to the object states rather than the function behind them. And finally, when it comes to action categories, I showed you this gradient from dorsal to ventral regions according to sociality and transitivity. And I showed you how different models explaining variability of these different actions differed between the LOTC, the IPL, and the ventral premotor cortex. So what does it all mean with respect to the ideas that I presented at the very beginning? If we think of this initial model that I presented before, that the generalization across the way we perform actions is hosted in the motor system, if we put all these data together, I think this explanation doesn't quite hold. So perhaps it is more realistic to think about this view, where both the ventral the lateral occipital-temporal cortex and the IPL contain both concrete and more abstract representations, whereas the premotor cortex and the IFG contain rather concrete representations that are there to for example, implement those actions, whereas the temporal, occipital, and parietal regions might be there more to anticipate what the best way of implementing those actions are given the perceptual input. And obviously, these areas interact with each other, so there's for sure more exchange about that. So where does that take us in the future? Let me spend 1 or 2 minutes on this region that I talked about quite a bit. So all of these areas indicated a certain role of the lateral occipital-temporal cortex, and that is perhaps not so surprising if you look at the literature from many different domains of many people also sitting in this audience. You see that this area hosts a variety of different aspects. So it is concerned about the representation of basic motion, biological motion. It's hosting 2 representations. It cares about body parts. It cares about the representation of hands. Stefania Bracci has done a lot of research on that. It's involved in action observation. It is involved, lately we've seen a lot of data that it's involved in action planning. There are a lot of studies from Jason Gallivan on that. We've seen that it also shows up in the representation of action semantics and action verbs. So if you put that together, there's something, what all these studies have in common is that they all cover different aspects that are relevant for actions, right? If you want to understand actions, you need to have a representation of biological motion, but you also need to have the corresponding semantics. This information needs to be integrated, right? And it's obvious, but we have a very poor understanding about how these different aspects that are relevant for action are combined in the LOTC. And that is due to the fact that we also have a very poor understanding about how they are arranged on a subject-specific basis. So this is putting together p-coordinates across many different studies carried out in different scanners and different participants. But I think what we need to understand is whether there's a consistent spatial relationship between these different aspects to get a better understanding of how this information is combined. And hopefully for the future, what we then can reach is, if we think about the way in which we categorize different actions, is that we think of a multimodal representation where we can describe which of these aspects are put together in order to distinguish between different actions, different categories that are perceptually perhaps very similar, but that have certain key features that are relevant for understanding those actions. So that is work for the future, and yeah, I told you I'm interested in studying this representation in more detail. I've given you evidence for a gradient of sociality and transitivity. There's evidence in the literature indicating that there might also be a gradient from concrete to abstract representations, and there might be more. And with this, I would like to thank for your attention. I hope you didn't fall asleep. And thank you in particular for all the people that were involved in this project. Thank you also for Alfonso for sometimes listening to me. And thank you for all the people that made this work possible.
So when you're viewing a visual scene and there's not really ever just one thing happening, right? So when people are transporting something, like in the picture, there's also things standing, right? There's people or animals looking around. If someone's giving someone an object at the same time someone's receiving an object, you can't have one without the other. So what do you think is the role of these regions in, say, representing actions that are happening simultaneously like that?
So just to make sure that I got the answer right, are you asking the question how we deal with the fact that in one particular scene there are typically quite a few different actions available?
Or even the very same participants, like if someone's giving someone something, at the very same time someone's receiving something, and you can't have one without the other.
Yeah, that's a good question. And in fact, I mean, if you think about object representations or scene perception, we have very similar problems, right? If I look at this desk, it's completely cluttered, right? And in order to grasp my glass and rather than the mobile phone, I need to focus my attention on what I'm about to do, right? And I'm assuming that for actions, similar things happen. Around you, there are people that are maybe falling asleep or can't be bothered, but I'm focusing on you, right? So regarding the opposing actions, there might be something special about that, right? Because certain actions have a counterpart that I might automatically activate together with that action. So I think I would like to distinguish between the aspect of having many different actions in the scene around, which I would assume is dealt with selective attention, and the counter or opposing actions that I would assume we're co-activating when we're activating that particular action.
I'm just taking the opportunity. Thank you for this very rich talk. I may have an old-fashioned question, but what do you think is the format of these abstract representation in LOTC?
Again, a good question. Based on my data, all I can say is it might be a very high-level visual representation. It must be high level because it shows all those generalizations across low-level perceptual features. But how far it goes beyond that high-level visual representation based on my data alone, I cannot say because I haven't done yet the generalization across materials, right? So for example, from one modality to the other. Something I'm planning to do, but I wouldn't want to lean out of the window to go beyond that. I would assume that once you're moving, once you're doing a generalization across modality, that what you see is more interior, but that I'm only speculating here.
So at least visual, I mean, something high-level visual. So
yes.
It means that we would move from something, so does it mean that it's also visual in premotor cortex, or do you think that it's shift from motor to visual? What do you think?
I mean, we know that premotor cortex has visual properties as well, right? So it's hard to exclude that premotor cortex has visual properties or shows these visual properties here as well. Again, I didn't do experiments to disentangle that. What I think of, if you're asking about the way this is represented, I'm thinking of a lookup table here, right? So we have all these different aspects. If you think of this slide here, I know that the print size is very small, but what I think of is that prototypical actions have certain features that matter a lot or that are distinctive for this particular action, right? So riding a bike typically involves a bike. Running typically involves a certain body posture. Eating involves available food. So I'm assuming that these aspects or the weighting between those aspects is represented somewhere, and this is what LOTC draws from, right? So, yeah. Well, I'm sorry, I'm taking over Alfonso's job.
Okay, hi. So I work in monkeys, and I work with physiology in the intraparietal sulcus, and we look at attention. And we find, and what we commonly find in these neurons is a multiplexing of information about visual selection, which is attention, and action selection. And I'm developing a bit of a different view of those action representations in the parietal cortex. From what I see in my neurons, it doesn't seem that action signals are there in order to drive action or even in order to represent action or categorize it. They seem to be there in order to instruct the attentional system as to what to attend. Because as you just alluded with your examples, we don't know to what to pay attention to unless we know what we're doing. So there has to be this feedback. I was wondering if you have any thoughts on this. I know it's an unusual perspective, but I wonder if you have any.
Thanks for that suggestion. I haven't studied that relationship yet between action representations on the one hand and attention towards those actions on the other hand. Perhaps the only example I can give you is the very first study where we specifically instructed participants to pay attention to the action or to the object. And what we saw there is that in more posterior regions, it matters less, apparently. But we haven't done a careful investigation to really clearly disentangle that across those different studies. And I think you're right, they must somehow act together. And at the moment, I cannot clearly dissociate them. I agree.
Thank you for this really rich talk, and I actually have a clarification question because I was not quite sure I got the way you have separated social and transitive, because in taking is I suppose it's transitive because it's object directed. But it's also social.
Yes.
While a gesture is supposed to be intransitive. However, from a certain point of view, if you think whether it relates to a change of state, its communicative goals are different from instrumental goals because they change the other's mental states, but they're still goal-directed and in a certain sense instrumental. But certainly there is a change of state, but especially in terms of the giving, taking versus gesturing, agreement, disagreement, I don't see how you can capture that as transitive, non-transitive.
I see your point, and I agree that there are different ways of manipulating transitivity and sociality. We were bound a bit here by our goal to have the stimulus material comparable across both dimensions. And this is why we went for this compromise. I agree that if you say only wanted to study sociality or only transitivity, then there would be more degrees of freedom of choosing those actions, right? I agree that the definition of sociality and transitivity is not necessarily what everybody would agree on what depicts transitivity or sociality. So in that sense, I agree that this requires follow-up, but I think it's a very interesting first step in that direction to distinguish between two different categories. And what they might be, we can define in more detail.
Thank you very much for this very impressive work. I've got a more fundamental question which does not only apply to your work, but I think to how the field currently develops based on this representational similarity analysis. So the question is basically, is it really useful to think about semantics in this sort of multidimensional geometric space, right? So, I mean, it's even worse when you think about like animals and tools, and then people are asked to rate on a scale between 0 and 7 how similar is basically a frog to a chair. So is that really that in our mind people have a dimensional space? I would doubt this. I mean, this goes back to the work by Tversky and so on, having like more a feature-based model, right? And also, like, I mean, Tversky already pointed out these ideas that actually if A is similar to B, not necessarily B is equally similar to A, and the triangular inequality and all these things. So that's why I feel actually this representational similarity analysis might not be the most appropriate tool and approach to look at all this, both at the behavior level, doing this sort of similarity rating tasks, and secondly also when using the neural representations, right? Just using correlation analyses. I mean, I know later on you do like a clustering analysis on top of it, but it's sort of like that I think the field should maybe move beyond that. And also that even the tree-based clustering also misses out on certain things that, for instance, they are like multiple. So for instance, you can have like two superordinate categories that define a subordinate category. The tree-based clustering doesn't allow for this. So I was wondering whether you have some views on that.
Yeah. Thanks for bringing up this topic, because we've been thinking about exactly that topic a lot as well. As you saw, the models explained a significant portion of the data, but not a lot, right? And that indicates that our models are, at the moment, a very poor description. So we're exactly doing that right now to look at more feature-based representations and see whether the dissimilarities that we're getting, first of all, are comparable to the semantic models, and whether they capture the data better than the semantic or the other models. And it's too early to say. It's very, very early work. That's why I didn't present it here. But I agree that if we want to have a fuller understanding, we need to also look at the more feature-based representations. And whether that should be done with RSA or another method, that's yet another question. I agree.
Angelica, beautiful talk. So, you know, you talked a lot about different levels or different types of representation, but you also use this term of gradients, which is becoming more and more popular. And I just want to maybe get you to clarify what you mean, because one, you know, fMRI data is particularly apt for demonstrating gradients because we have voxels and we average across it, so it's really conducive for giving us data that looks like a gradient. Also, the tasks that we use, because of our inability to clearly separate out what you think is social versus transitive, for example, also might give you some smearing. Versus the more, I think, important or deeper question about the neural organization. So, which, you know, if it really is a gradient at that level, that has really important and maybe profound implications for the way we think about brain organization, right? So, when you were using that term, what did you mean by a gradient?
So what I mean by gradient, and I'm happy to define it in a term that perhaps is more appropriate, is that the representation of certain features varies across space in the brain. Whether or not there's a categorical boundary or not, well, I cannot exclude that with my method, right? But what I do see is that there's a variation across space.
So does that mean a mixing of features and properties?
I would be certain about that. Obviously, with our 2x2 or 2x2x2 designs, what we see is the representations of those features in that particular area. But I'm thinking about the LOTC.
Well, I was going to use biological motion, for example.
Yes.
So we know there's a lot of evidence for posterior STS being particularly responsive. So in this kind of a view, you see those cells that are particularly responsive to biological motion being, what, smeared into middle temporal gyrus, for example?
So what I'm thinking of here is very similar to what Michael Graziano described in the motor and premotor cortex. I'm thinking of various different gradients sitting on top of each other. I don't think that there's one particular area that is only doing biological motion. I think that these different patches are used for many different aspects, and in our experiments we tend to see only those that we investigate, but they're used for many different things.
You alluded to the cross-modal question, but I just wanted to hear a little bit more about that. So just to make it concrete, if you, again, have a person then hear sentences describing opening and closing, you don't expect you'd be able to see any, that this model would be able to pick that up in these LOTC regions? We haven't done that experiment yet, but I would be surprised if you wouldn't see it in LOTC, but in the more anterior portion. Wait, so that's two different things you're saying. So you're saying that it could be more anterior, meaning that it's where it becomes more modality independent, but would you also be able to expect to see it in the areas that you're talking about today? Well, we haven't done that experiment yet. I would assume that there must be a transition phase where you see both. And I'm thinking again of if you want, gradient, where you go from a more purely visual towards a more modality-independent representation. And I'm assuming that there's an intermediate stage where you have both. So they need to exchange information, right? I guess I think that the feedback connections, though, might still, it's not a high bar here, right? In the sense that the classifiers are at like 54, 55% or something. So maybe you wouldn't see it because there's just so little window there to be able to detect that. For that, I haven't shown, I think fMRI is also limited when it comes to terms of temporal resolution. So for this, we need to also move more towards MEG, I think, if we want to talk about connectivity and feedback, if you want.
I see. So
Yeah.
just one more quick thing.
Yes.
So if you don't see it in, if you couldn't get there through the, say, auditory modality, then I'm just trying to get a sense of what abstract visual might mean then in that sense. That you can pick it up, that doesn't pick up abstract at the sort of
Right.
modality independent level.
Right. So what I think of as abstract but visual is similar to what you see in the object domain, that you can represent, say, a bottle, irrespective of the shape of the bottle, of the size of the bottle, of the viewing angle, right? It's still in a way visual, but it shows generalization. And I'm thinking of very similar features or properties in the more, in the LOTC, that we show that we see this generalization across certain aspects of the action, but it might still be at a very high level, perceptual level.
Thank you. Also, I agree with everyone. Great talk. I think I might have a question related to Rich's, which has to do with this notion of abstractness versus concreteness. So, I mean, another possibility, I think language researchers sitting in this audience might interpret your data very differently. That would be, in other words, it's not necessary that you're getting some kind of abstract visual notion or movement-related notion. It could also be that some of your results, at least, are driven by inner speech or semantics, in the sense that it's not, you used visual stimuli, but of course the big test will come when you do a similar experiment using language-related stimuli. So things are not driven visually. So that's one point, is about the posterior, the quote, abstract representation. Are people saying bottle to themselves? And then the question, of course, it begs the question of, well, what are they thinking then? Are they thinking of some kind of canonical bottle-like thing that would describe all bottles that they've ever encountered? How embodied is that, is sort of what we're getting at. And then with regard to the PMV representation, I think some people might at least say that what you're getting is not concreteness per se, but you're getting a more high level of specification requirements, selection requirements. So you're having to narrow in, and you're driving your semantic network to pick out one thing which is going to drive that network. Now, of course, you might argue, well, that's not supposed to be PMV, that's really supposed to be IFG, but it's so proximal to that maybe that's what you're getting. Rather than abstract to concrete, you're getting sort of more general to more specific.
I would agree with that.
In a selection sense.
Yes, I would agree with that, and I would be happy in even using those terms. For me, I'm using abstract and concrete here in the way of general, in terms of shown generalization versus being specific, not showing that generalization.
I just think it's very important to be really specific about our terminology, because abstract means something really different to it really is a claim. So that's all. Just be careful. Okay.
Was there a question?
I want to follow up on the abstract. In the way you defined abstract, which was generalization, representation that generalizes across different shapes and sizes and so on. So when you went through the first several data slides and you looked on the, the areas that were on the right of the slide, like lateral, occipital, temporal, in addition to seeing generalization that you referred to as evidence of abstraction, in all of those slides, you also saw that in the concrete test, it was greater, right? And so there's two non-mutually exclusive formats that could get you to that result. One is that there are commingled concrete and abstract representations of the information there, and the other is that the abstractions are actually more similar to one another when you have the exact same object than when you don't. And I was wondering which of those is, and if it's the former, these kind of commingled concrete and abstract representations, what you think that says then about how abstract this actually is.
Yeah, that's a tough question. I'm not sure if I have an answer to which of these two solutions that you just proposed it is. If I think of the information that is hosted in this area,
I'm assuming that if we think of a communication between LOTC and IPL that has been shown in previous studies, that it is helpful to have both a concrete, or say, let's use the term specific, that you have a very specific description of this particular bottle. If you plan to grasp it, this is the size of the lid, and this is what I would do with that. At the same time, to also have a very general description. If you were to grab any bottle, this is how you usually manipulate bottles based on my previous experience, right? So I'm more thinking about the two representations sitting next to each other because we use them for different purposes. One for the more theoretical aspect of I'm seeing a bottle and how do I normally manipulate bottles, and that's something you might co-activate in case you decide to manipulate it. Whereas in comparison to a very concrete case where you plan to grasp that specific bottle and you really need to provide the parietal cortex with an instruction, look, I think this is what you should do, and the parietal cortex then recruits those motor programs and sends it to premotor cortex. That would be my reasoning about your question. Well, whether it's the same population or two overlapping populations, I wouldn't know. That requires more studies, I would say. But interesting question.
So you're thinking about these action representations both in terms of what the person needs to do to plan action, and you're thinking of recognizing actions in that context, and obviously that's a good way to think about it. Mm-hmm. But there's another way of thinking about representation of actions, which is just in terms of explanatory understanding, mm-hmm. so that you can predict or explain. And a way of separating those two is to look at the representations of actions that people can't do at all, mm-hmm. right? So we make sense of animal actions, we make sense of you know, imaginary actions of imaginary alien beings that we can't possibly do, but yet we still can explain them and represent them. And I wonder, and this has to do with the whether it's necessary that the representations of actions that guide our categorization of them are embodied in the way that of course the actions that we can do are, right?
Yeah.
And so have you considered at all looking at the representations of actions of like I don't know, spinning a web or I mean, you know.
Yeah, no, I haven't done that. I agree with you that that would be a very interesting distinction to add. I'm thinking of data that Alfonso collected together with Jill Vanuskorp on participants that were born without their upper limbs, right? And it's very unlikely that they have developed motor programs for their own arm movements in the lack of arms, right? And yet, as they have shown in a number of studies, is they have no difficulties recognizing or predicting movements of the arm. So I would take that as evidence, at least for those movements, that perhaps it is not a requirement to simulate those actions. It might be different for more complex actions like playing a violin, but at least there's evidence against that. Yeah.
So I just want to follow up on Alex's question and this notion of gradient. So one can imagine a functional gradient, like we've been talking about, if there might be levels of abstraction and there's a kind of gradient that way. And one can also think of anatomic gradients, which seemed like you were suggesting. And the question is, when does one gradient map onto the other and when not? And I'll do this by a silly analogy, which is in Philadelphia, Independence Hall is where the initial Congress was, and representatives of the 13 colonies sat in an analog representation, which is the Northeast was over there and the South was over there. And so they're representing their analog states, and they're representing it in an analog fashion in Congress in a way that currently Congress no longer does that. And so the question is, when a functional gradient also maps onto an anatomic gradient, and when it doesn't, what's at stake?
So again, I cannot, based on my current data, answer that question because I haven't done the analysis of anatomical connectivity and functional connectivity. That's something we're working on right now, and I would assume that I'm thinking of the anatomical connectivity as the highway system that we're exploiting using task-based activity. So I'm assuming that the anatomical connectivity gives us what we're, well, the functional connectivity in a way then tells us how frequently are we using those highways, right, for certain tasks. So for me, they go hand in hand, and that is exactly what I'm planning to do for the LOTC, to study both functional and anatomical connectivity. I don't think that it makes sense to only interpret functional connectivity without also looking at the underlying anatomical connectivity, knowing that functional connectivity measures using fMRI are also quite variable and, yeah, error prone. I don't know if that answers your question.
There were other questions, but thank you very much for all the questions. I just wanted to make one last comment. I think that what has come out, aside from the beautiful empirical work you've been doing, perhaps the most interesting aspect, given the discussion, was what models do we have? And no offense meant, but we don't have any good models.
I agree.
We don't have any good cognitive models. People are talking about the brain perhaps prematurely. That is pointing to parts of the brain that do this and that is interesting, but we have to have a correspondingly clear analysis of the cognitive processes. So what does abstract mean? What does concrete mean? What does action mean? And it seems to me, and again, no offense meant because I do the same thing, we just have no idea what we're talking about. So if you, at least if you look at language, you can say, well, we can piggyback on the linguists. They're struggling, trying to come up with some computational analysis of language, which we can borrow. Perhaps it's wrong, perhaps it's got all kinds of limitations, but it's striving for an articulated view that makes sense of the components that it uses. That is, it has a vocabulary. We don't even have a vocabulary. So when we talk about visual representation, we have no idea what we're talking about. No visual scientist can tell you what he means by visual representation other than it responds to a visual stimulus. Now that can't be enough to have a theory of action. So many of the comments that were made are perfectly fine. I don't think they're directed at you as much as at us, the field. So I think that we can take this presentation today, which I think was great, I agree, it was a beautiful presentation, really as a warning signal. All this beautiful empirical work, for what? Are we going forward to making a real articulated theory of action representation? And this really requires an integrated approach. It can't be left to the neuroscientists. They have no idea what it means to act. Nor does it leave it to a cognitive scientist who has no idea what the brain does. I mean, so I'm not trying to say one side is good, one side is bad. What I'm saying is that to do this kind of work, we have to do the hard work of trying to develop the theories. Thank you very much for a beautiful presentation.
Thank you.
We have coffee break. We have coffee break, and please come back by 11:15 or thereabouts. Not much later. Sorry? And post the session. Thank you. And post the session.